Hi, folks. Welcome back. Welcome back. So, quick recap. Hopefully, everybody is working through their projects. I've emailed folks feedback. I've also assigned people to a primary TA. So please start meeting with folks. Folks, hey. All right. So please start meeting myself and the primary TA maybe every other week, so that every week we have someone to update and give feedback. And hopefully by now, you finalize your main ideas. You have this experimental setup, meaning your data set, your models, where your baselines are, already started maybe getting some of these baseline models working and making some progress towards your initial ideas. So next checkpoint is after spring break. That week, on Tuesday, your midterm report will be due, and on Thursday, we're going to go through and folks are going to present during Thursday's class, the week after spring break. All right. We also released the reading assignment. That's reading assignment 3. It's going to be due tomorrow evening in preparation for this Thursday's class. This third reading assignment is on multimodal alignment. So different ways how you can align modalities to common representation spaces. That was this contrastive learning paper. How do you do that? They showed some nice analysis. And also this second paper called platonic representations, which is basically this interesting phenomena that even without enforcing alignment using contrastive learning, just by scaling up models and training them independently, some alignment and similarity emerges. They might be converging to this, unified similar representation. Also a very interesting phenomenon. Both of these papers leave a lot of open questions, and hopefully we'll discuss some of that this Thursday. Okay, so today we looked at introduction to multimodal learning, we looked at multimodal fusion alignment, and today we're going to dive deeper into multimodal fusion. So this challenge where different modalities and you're trying to fuse them together. And the general definition is that you learn given two modalities, some joint representation that is able to capture how these modalities interact, where the information is coming from, and how this information combines. And again, go through this whole space of multimodal fusion in one lecture. The goal is to get a sampling of different ideas and this whole spectrum of ideas. Whatever ones that are most relevant to your project, probably dive deeper and look at those individual papers. So again, I think about fusion as a spectrum, right? You can either take your data in its raw form, your raw modalities, learn some abstractive features by using pre-trained models. And once you started extracting these features, your modalities are in more abstract form and are therefore more likely to be similar in nature because you're comparing them in representation space. So then the fusion will be on these abstract modalities, and the fusion has to do less heavy lifting. And fusion is typically simpler. And another paradigm for fusion is when you're starting with raw data, so triangle, circle, raw data modalities, and therefore these raw data modalities can be more different from each other, more heterogeneous, different dimension, different discrete and continuous space, different elements. All the reasons why we discussed modalities being different. And you will fuse it earlier and let the fusion model do more heavy lifting. So one side is where you extract features first independently, and then you do something simpler in fusion. The other general paradigm is you don't extract any features, start with raw data, and do more work in your fusion. And again, this is a spectrum. We'll cover methods that really span one extreme to the other extreme. And the whole goal in fusion, again, I highlighted this term, is to capture the interactions between modalities, the fact that these modalities combine information in some way. And recall during last lecture, we introduced this idea of multimodal interactions as one of the 3 key principles which makes multimodal data unique. Intuitively, how these modalities combine to provide new information for a task. And we discussed several types of interactions. The first one is when there's redundancy, where there's common information. So you might say something happy and show happy expressions, and both of these really reinforce that this person loved this movie. And we also looked at alignment methods, and we actually showed, we gave these examples showing that contrastive learning, they essentially learn separate representations and brings them together using some similarity function, called that contrastive function, will actually provably learn the common information between them. Right, so there is this intuitive connection between alignment-based methods that we saw in the last lecture and redundancy. So the alignment-based methods essentially capture the redundant shared information between modalities. Again, these are all intuitions. There are no really formal proofs or anything, but if your data is mostly redundant and you're trying to capture this common information, an alignment-based contrastive learning methods are something that you can explore. Which therefore leaves two other interactions that we also saw. One is uniqueness, so there's unique information in one, not present in the other. For example, you're saying something positive, but this isn't also what you're showing in your facial expressions, which are neutral. Then you can actually show that these alignment-based methods, based on contrastive learning, they will only learn what is common, and they will throw away what is unique. So some of the methods we look at today will look at how do you better capture this unique information. And also this third type of information, which is synergy. So the information isn't common in both, isn't uniquely present in both, but only arises when you start fusing these modalities together. So some examples that I gave was showing something positive in what you're saying, but you're showing some anger or frustration in your facial expressions. And together you get the idea that a person is actually being sarcastic. So again, alignment-based methods will just really not capture this. It will just capture the common information. So we'll discuss ways of doing fusion to capture synergy. So the whole idea, multimodal fusion is to capture these different types of information, ways that information merges together when given multimodal data. So you saw this spectrum, fusion with more abstract modalities. So this is the case where you first extract some features using pre-trained models, and then do something simple in fusion. So for example, you could extract image representations through image models, language representations using language models, so word to vec, BERT, language model, and so on. And these encoders, the main intuition is that they're taking in raw data and they're extracting some more abstract features. These features should have some semantic meaning. So they might be dog meaning over here and dog meaning over here. So they're more similar semantically, and you can start doing less work in fusion. So this also mirrors what some other people call early and late fusion. Early fusion is this idea where you just take your data, combine it in some way, and then put it through some model. So you're fusing your data early on, so directly combining your data and letting the fusion model do more work, versus late fusion, in which case, at one extreme, you can even extract the label, so make the prediction from modality A, make the prediction using modality B, and then just combine the predicted labels in some way to get the final outcome. So people have explored, for example, ensemble methods, taking a majority vote. If you have three modalities, two of them say one label, the third one says some other label, you just take the majority vote. These are all examples that fall under late fusion. All right. So these are just sampling of methods. So I'm going to start simple and just really introduce some basic concepts of fusion. So we're going to, again, the idea is to model these cross-modal interactions, the ways that these two modalities interact. And we're going to just start simple by looking at the one-dimensional case. So modality X1, just one dimension, modality B, one dimension, and the label one dimension. And one very simple way to introduce the idea of fusion is to just look at the linear case, where you're training linear functions that take in your data and make predictions on a label. So I think all of you are familiar with linear regression, where you have your label y equal to some intercept, w0. So this is your intercept where it intersects the x-axis. There is some weight w1 on xa on the first modality. There is some weight w2 on xb, which is the second modality. And you have this interesting term, which is this w3 term of xa times xb, right? So you can think of the first two terms as additive terms, each of the modalities contributing independently, weight 1 times the first, weight 2 times the second. And you want to think about this additional term they've introduced as this multiplicative term, or we call it a multiplicative interaction. We first take the multiplication of the two modalities and then determine what is the weight W3, which is useful to predict the label. Okay, so to see an example of this in practice, let's just say you have this this task where you're trying to make predictions on book reviews. So there's two inputs. Okay, so the context is that there's some people who are saying, I read this book, it was very good, I like this, I read this book, I didn't like these characters. So these people are saying some stuff, and I'm extracting two modalities. The first modality is just the percentage of time that the people are smiling when they are speaking about this book. They can be smiling all the time, or they can be not smiling at all. So that's a continuous value. And then maybe the second modality is just this indicator variable that represents whether it's a professional critic of books. So they criticize and review books for a living, and non-critics, so just everyday people like us. And label Y is what the actual score. So the ground truth score of, kind of like Rotten Tomatoes for books, or it's a score for those books. Okay, so it's a simple problem, XA, XB, and some label Y. And to see really these things in action, you might have several things you want to predict. First, you might be interested in whether the percentage of the time that a person is smiling is predictive of how good or bad that book was. Right, so that's maybe the first hypothesis. And that's, you can tell, that's very much a unimodal hypothesis, right? It's just looking at XA and how that influences Y. And then the second hypothesis is a bit more interesting, which is that does the effect of smiling depend on professional status? So now you're asking a question about how these two modalities interact, right? When I am not a critic, I just review books as a hobby, what does my smiling indicate about how good the book is? Versus when I'm a critic and I'm doing this for my occupation, what is the effect of smiling on how good the book is? So you can do some basic analysis. You can just train these regression models using one modality. You will start seeing that, let's say XA is how much you smile. And of course, that will be positively correlated with how good the book is. So it's a positive slope between XA and Y. This could be your estimate with some intercept over here. So you can not smile when the book is about average, 4.6 out of 10. And then you could also imagine training linear regression with both modalities. So weight times XA plus weight times XB. And intuitively, your line that you get will be something like this, where because B is an indicator variable, it can take in either 0 or 1. So these two lines would have the same slope, weight 1, both are positive. It's just that whether the person is a critic or not shifts this slope up or down. Right? So if they're not a critic, in general, they are higher, but the slope is still the same. And if they are a critic, they shift down to something lower. So critics might be more harsh on books, essentially. So that's an example of linear regression without a multiplicative plan. The gradients are both W1, and the second modality only introduces a shift up and down of that curve. All right. And now see what happens if you maybe start fitting linear regression with multiplicative terms, with W1XA, W2XB times W3 on XA times XB. Now, naturally, you'll see that your function is more expressive, and it could capture pairs of functions that are no longer the same gradient, no longer just shifts of each other. And the way you want to interpret this function is that, okay, when the person is not a critic, that's their baseline. This is their slope. And now when I introduce people who are critics, if the critics smile more, they like the movie even more. If the critics smile less, they like the movie even less. So they have bigger extremes versus just a normal person. And this could be, for example, one fit that you have. So W2 negative, critics in general are more harsh, but then this W3 multiplicative effect essentially tells you that on the extremes, these critics are much happier when they smile and like the movie much more, and much angrier if they don't smile. They like the movie much less. So that's the intuition. And again, your answer to this hypothesis is that yes, in fact, the slope of the line does change, right? The slope between how much you smile and how the movie was is different, whether a person is not a critic or whether a person is a critic. Right? So that really just motivates, basically why people want to take multiplicative interactions into account. And that was a one-dimensional case. You can extend this to a higher dimensional case. One common way of doing it is to essentially, to take your data and, for example, capture these interactions by multiplying them element-wise. So if you have four-dimensional data, XA, four-dimensional data, XB, you can learn a diffuse representation Z by doing element-wise product between XA and XB. So this will be at every dimension, a multiplicative interaction between the first and the first, second and the second, third and third, and so on. Of course, if you get even more expressive, you could take in four-dimensional data XA, four-dimensional data XB, and create this matrix, which is 4x4. And you can think about these as bilinear matrices. We're taking essentially this, every one of the elements in A, multiplying every one of the elements in B. Right, that's how you get this 4x4 matrix, essentially capturing these multiplicative interactions between all pairs of features in the first and features in the second. And if you look at this bilinear fusion, you might be reminded of something that we saw last week, where again, you had these two vectors and you took some outer product to get this pairwise matrix. And that was these multimodal transformers, right, that we saw last week. So in fact, a lot of these modern transformer architectures were inspired by these more earlier bilinear, we call them bilinear pooling. And again, the idea is to take all pairwise combinations of one set of features with all in another set of features. So multimodal transformers does something quite similar, but with some subtle differences, as we'll see. You might have data from the first modality, say a couple of words that a person is speaking, and that may be 3 words by some dimension. You put it through some linear transformation. You have data from the second modality, maybe the person's facial or vocal expressions. That might be another set of features, but again, the sequence length might be different. So I wrote it as 3 by 4. And you're essentially taking this product to get this pairwise multiplicative interactions. Right? For every one of the words of the 3 words, by every one of your 4 visual or vocal expressions, you're trying to learn how much to interact with each other multiplicatively. So that'll be your 3 by 4 weighted outer product. Same stuff, normalized by dimension d, square root of d, to a softmax. So each of these values can be interpreted as probabilities, and then take the multiplication with the actual features in the second modality. Right, that allows you to learn a new set of features. These are new features for language. There's 3 of them, 1 for each of the 3 words. But now for each of the words, you looked at the probabilities with the 4 nonverbal expressions and actually multiplied by the 4 nonverbal expressions. Right, then you use it to predict some sarcastic label or something. So these multimodal transformers and the previous slide that I showed on these like bilinear products, essentially all operate on the same idea. You have multiple features, and you're looking at how features interact pairwise with another group of features from another modality. Did you raise your hand a little bit?
Yeah, I have a question on the last slide.
Yes.
I'm not able to understand why the transposers are not
So think about it as matrix dimensions. So these are typically things that 1 by d. So maybe I'm just showing one data point here. So 1 by d, 1 by d. How do you get some output? So in this case, this is just element-wise multiplication. So 1 by d, 1 by d. The first element get multiplied, second element get multiplied to the 1 by d. Over here, what we're doing is that this is 1 by d. This is also 1 by d. But you want this output to be d by d. Right? So the first 1 by d has to be transposed to d by 1. And then this 1 by d. So essentially, every one of the d's element-wise multiplied with each of the other ones in the other d dimension to get d by d matrix. Oh, so this is just more expressive than this, right? Because over here, it depends on where your features are. Each of these features can only interact with the features in the same dimension. Here you're looking at, for example, the first and third interacting together. So again, it depends on what the features are. Sometimes it's very important, sometimes it's not important. It depends on the problem. Yes.
Thinking of in also to the temperature of dynamic interaction between the dimensional. But we have like a clear understanding that this dynamic interaction. There are important. There might be like multiple interactions with the dimension of the need like more than 2 to 5 interactions with the something that's relevant for our data. And we all we still need to see the dimension.
Very good. Yes. So this is what this slide will be about. So we saw this case for 2, and I'll get to that question very quickly. But let me just wrap up the 2-dimensional case. So we saw from this in a previous slide, if you take XA 4 dimension, XB 4 dimension, and you take this outer product, you're only ever getting these multiplicative factors. Each of the factors is XA times something in XB. And sometimes it may be useful to also keep the unimodal factors. So some XA and some XB, these are independent unimodal factors. And one trick that you can do is to append a 1 to your feature vector before taking this outer product. So what this will look like is now 5 by 5, which has a 4 by 4 subpart, which is the multiplicative, You have 4 by 1, which is just B, 4 by 1, which is just A, and a 1 by 1, which is just the intercept. Right? So that's a cute way of getting the multiplicative terms, the two individual unimodal terms, and the intercept. And then, of course, to your question, yes, bimodal, unimodal, and the intercept. And to your question, of course, you could go higher with many problems with 3 modalities, 4 or 5. And you could start again doing this, and now you get this tensor. You get essentially in 3 dimensions, you get a 3 by 3 by 3, or it's 4 by 4 by 4, 3-dimensional cube, which is where the 3-way interactions are. You get these spaces, which are 4 by 4, which are just the 3 choose 2 pairwise interactions. You get the unimodal interactions, and you get the 1 at the end. So you could go more expressive. Yes.
And just to kind of, doesn't it be like multiple modalities, right? Like, for example, the image and the sound in that modality, and the 2 corners of the image and the sound is interacting to self-repeating with the image modality is whatever the scene is later or other capturing this like multiple types.
There are ways. So again, these are plug and play. You can modify. So for example, you could say, I have image, but maybe the image is very important. So maybe this would be the one corner of the image, maybe some other corner of the image. You could even do modality A and modality A by itself and do these interactions. Just really depends on what the problem requires. The good thing about all these are basic mathematical functions. They are reasonably efficient to compute. They're differentiable, so you could just plug them into any layer of your neural net and train everything end to end. Speaking of efficiency, you will start to see that, at least in a 2-dimensional case, it's still reasonable. So some of these, transformers also do this pairwise, 2-way pairwise. But once you get into 3 and 4, it becomes very big, very inefficient. And all these weight matrices will end up quite large. So how to make it more efficient? There has been a new set of methods called low-rank approximations to these large matrices and tensors. So if you look at a 2-dimension case, the vector coming in, 4 by 4. So this matrix of 4 by 4 is the one that captures these multiplicative interactions. So this one is still not that bad. It's not too much, maybe 60. The issue is that if you put this as a layer in your neural network and you want to get it to the next layer, maybe this next layer is 10, for example, 10-way softmax, then you need this weight matrix that does transformation from this 4 by 4 to 4 by 4 by 10. So this next weight matrix is actually the one that is much more computationally expensive. So there's ways of essentially making these more efficient by not learning a 4 by 4 by 10 matrix entirely, but rather assuming that this matrix has some low-rank structure. Low-rank structure meaning it's approximated by maybe a combination of smaller matrices. So several ways of doing this. First, decompose this weight W by assuming it has some low-rank structure. Instead of creating this entire 4 by 4 matrix, we can implicitly just leave it as these 4 individual vectors. And you can provably rearrange this computation into something like this. You're still keeping the 4 by 4 individual vectors, but all these individual things are just submatrices that we have decomposed this large cube into. One intuition of thinking about this is that, let's say you have a matrix that is 10 by 10, right? There's maybe 100 parameters, but maybe some of these dimensions might be related and correlated with other dimensions. So you can approximate this 10 by 10 matrix as a bunch of 10 by 10 outer products summed up together. If you just do 2 summations, it's 10 plus 10 times 2. So that is just 40 dimensions instead of 100 dimensions. These are called low-rank approximations. So visually, what it looks like is you would take in this big cube and you would maybe decompose it into a limited sum of these outer products. So in this case, I'm just showing 2 of these sums. If you have enough summations, then in limit, it will approximate all possible cubes. But you only have 2 sums, and it can only approximate a small number of these cubes. But in practice, it's efficient. And now you see the number of parameters reduced dramatically. And you rearrange this computation by essentially not creating this 4x4 matrix and leaving it as your two individual vectors. And you can show that this final computation is equivalent to taking these two factors and multiplying it with the first matrix and these two factors and multiplying it to the second one. Looks something like this. Just some cool visuals. Again, you all can read up some of these details, but these are, if you want to do something efficient, just search low rank approximations. They're used in multimodal learning. They're used in fine-tuning LLMs nowadays. So all these big LLMs have, attention heads, which are 768 by 768 large matrices. You can, instead of updating the whole matrix, you can just update some low rank approximation of that matrix. Similar ideas. So I included some references. Great. So I think up to now what you've seen is that you can start with very simple vectors of your data and then compose increasingly expressive multiplications. There are 2x2, 3x3 multiplications. You can go higher and higher. One thing people also do is they might take polynomial factors. So something to the power of 2, power of 3. All this could theoretically make your model more expressive and therefore more likely to learn more complicated interactions between modalities. But then you also always have this issue of, am I doing too complicated of a model and therefore overfitting to my data? And that's a bad thing. So you gotta find some place to stop. And one thing people typically do is to basically just check your generalization using cross-validation. All right. And everything that we've seen so far, you have two modalities. We're essentially creating this weight matrix that is static. It's always just the same across all your data points. And then there's this new generation of methods which are called gated or dynamic, in which case the features that you actually extract from the modality would depend on the modalities themselves. So there's this kind of gate that's going on, where given the current modality, you will learn some attention weights over yourself. And given the other one, you will learn some attention weights over yourself. And these attention weights could differ because it depends on the current data point. It will differ across different data points. Sometimes information is very useful, and these are ones and that things pass through. And sometimes it's not very useful. You will learn things like zeros and will not let things pass through. Again, very reminiscent of these, self-attention mechanisms in transformers. So you could think of these things as, previously we saw your output was just a fixed weight W1 times XA plus W2 times XB, and the weights W1, W2 was fixed. But now these weights W1 and W2 depend on some function G of your current set of inputs, right? Instead of just having fixed W1, W2 weights. You can view them as attention functions, you can view them as gates, and it's a lot of exploration on how do you condition these gates? You just look at the current modality, you look at both, you look at more things, you look at the context and so on. All these is just to better design these dynamic weights. Great. More stuff on gates. These gates can be done using soft attention. So these are, for example, a softmax that tells you everything between 0 and 1. And it can also be done using hard attention. Hard attention means it will literally just be 1 and 0, be discrete. So you will just let this feature be used for the fusion or not let this feature be used for the fusion. Nothing like it would be used like 0.5 for the fusion. So hard attention would make things more interpretable because you're literally selecting subsets of features to fuse, but the difficulty is that it might be harder to train because it's discrete. Okay. A little bit more complicated. Up to now, we've seen essentially fusion where your modalities were symmetric. You always say XA, XB, and some function was being operated over them. But in many cases, we have some prior knowledge about some modalities being more useful and some being more secondary. One example is just human communication. Right? We know that 90% you're just listening to what the person is saying. So XA being language should be primary. And maybe the remaining 10-20% of the time, you might look at facial expressions or voice, only when it's really necessary. So you have those kind of scenarios. You might not want to do some symmetric fusion. You might try to have one as a primary and only use the other secondary modalities as a way to make minor modifications, minor changes to the primary one. So one set of methods that have come out is take the secondary, in this case, visual and audio, and you learn some function that tells you how useful they are, and that gives you some set of features. Sometimes they're let pass through, and sometimes they're just zeroed out. And then you would just use that as a way to modify representation from the primary modality, which is language. And intuitively, you can think of it as a space where the centroid was your language embedding, for example, word embedding or sentence embedding. And most of the times it's just there, but it will be shifted in small directions depending on what the nonverbal expressions are. So one way to account for the fact that some modalities are more dominant than the others, and therefore more efficient. This fusion on the secondary modalities could be smaller, more efficient. Okay. Great. So we went through a journey of data coming in, various forms of fusion methods, becoming increasingly complex. And now on the other extreme, there's really basically methods that take in your data XA and XB over here, and essentially just concatenate them as early as possible, and let the fusion model figure out what the fusion should be. So we call this kind of early fusion. You're fusing it as early as possible. So XA and XB would just be, for example, concatenated as early as possible. And then you would just define a bigger model F to let the model basically figure out, without much human engineering on the features, what the fusion should be. So this is also very common nowadays. We'll run through some examples of how F being multimodal transformers and so on can be used for this kind of fusion. But before getting to that, let me also cover a paper that I like really much, which is you could define these complicated fusion strategies. But the question is, will our model actually learn what these interactions should be? Because the hope is that your model learns something really interesting from these two modalities, some really interesting synergy or interesting interaction. That's why you do all these multiplicative stuff, your tensor stuff, your transformer stuff. But then, will a model actually learn these interesting interactions? Yeah.
Is the underlying thing something that could be represented as a function in the examples that you're going to show? Does that make sense? Is it like a squiggle kind of like if you were just thinking about, or is it like quadratic or something? So we're saying nonlinear here. Is that question one?
Yes. And I'll get to that. Yes. So linear interactions are things that are just the form f of a plus f of b. Right? These are what we call linear interactions. So there's nothing these two modalities are actually bringing together in conjunction with each other. So you train a predicate on A and you train a predicate on B, you add them up, and you're done. These are linear interactions. So nonlinear interactions is anything that is beyond this. Right? If, for example, they have to be multiplied together quadratically, if they have to condition on each other, if they have to be fused in some synergistic way, those are nonlinear interactions. So one way of essentially measuring whether your model learns these interactions is that, let's say you have some function f over your two modalities that you claim is super awesome. Then what you can do is essentially find a closest function to f that is only linear in nature with respect to f of a and f of b. And what we do is that we do a projection. You're basically looking at all possible, these are your fancy models, for example, neural networks, LXMERT, these are pre-trained vision language, BERT-like representations, kernel SVMs. These are all your complicated models. And I'm just projecting them into this space of models which are just additive. So f of a plus f of b. Okay, so finding the nearest neighbor inside that space. So how do you actually do this projection? Well, these folks proved that if you have, for example, a function f, which is a complicated model, you can essentially do two things. First, take expectation over b. In this case, expectation just means I feed in a bunch of these into the model, and I take the average over it. So once you've taken expectation over B, in the limit, it will only be a function of XA, right? Because you're basically marginalizing XB out. And then what you can do on the other side is to take the expectation over XA. So give it a bunch of sentences, see what a model does, and then take an average over all of those sentences. So now you're averaging the effect of XA away, and it's just a function that depends on XB. So this way you can show that this is kind of the nearest projection from complicated models to the simplest additive model, f of A plus f of B. Okay? And these folks actually show that sometimes you have all these complicated models. Sometimes you can find their performance, for example, 91%. And if you project it to the simplest possible, these additive models, the performance only goes down to 91.1%. So it drops by 0.2%. And maybe some of these data sets, it was 81.5% with a complicated model. We found the nearest one that was just additive in nature. And again, it just dropped down by 0.2%. So sometimes, these really complicated models are great. Lots of fusion, lots of new information being learned. But sometimes they might be approximating nothing else than just simple additive combinations, f of A plus f of B. So this, I like this paper a lot because it kind of re-challenged a lot of the thinking, including some of my work. Yes. Best model over here.
Yeah. So trained the task using several techniques.
Yes. Yes, that's a very good question. So the fact that, for example, you took a complicated model and you found the nearest neighbor additive model and only lost 0.2% doesn't actually mean you can just train additive models from scratch and get 91.1%. And that's another subtle distinction they made. Because if you just train linear models, you don't really know what linear model it is. You don't know what your function space is. You can only get like 70%. When you take a complicated model and find the nearest linear projection, you may not lose that much of performance. So there is still value. You can think of this as an algorithm where you train something really complicated, and let's say you care about efficiency, and you distill that model into this nearest additive combination. So now you're efficient, you're saving parameters, efficient, and you're also getting some reasonable performance. Great. So that inspired some work that some of my friends did, which is to really force this model to learn these non-additive interactions in a stage-wise manner. So if you have, for example, 3 modalities, you can first think, I'm going to start incrementally training more and more complicated models. I will start with just addition of unimodal contribution, and then I will look at the pairwise, and then I'll look at the 3-way interactions, instead of just doing everything all in one go. So each of these would be called stages: unimodal stage, bimodal stage, trimodal stage. In the unimodal stage, I would just take the 3 modalities, extract features, define weights for them, and add them up. Right? So just a simple weighted combination of each of your 3 individual vectors. And then I would make a prediction y hat, unimodal. I will compute the loss, and I will optimize it. Right? So optimize the loss. And then I will see what is the remaining loss. So what is in my true label, ground truth, that is not captured by this simple combination of a 3-way unimodal. And then I will consider that optimizing for the bimodal. And only then I would consider optimizing for the 3-way. So each time I'm optimizing at the start, I'm just optimizing y, ground truth, with respect to my prediction. And then I take the difference, the residual. So what I was not able to capture from this unimodal, and I try to fit these bimodal models to it. And then again, recursively, I'm going to try to see what I could not find. So y minus y unimodal minus y bimodal. I only use the 3-way interaction to learn that residual. So call it residual optimization. And it's really cool because now you are essentially guaranteed to improve each time. Right? You're only ever optimizing your remaining 20% error. So that 20% is guaranteed to go down to 15%. And then there's 15% error left. We optimize this. This 15% is guaranteed to go down to something like 10%. So each stage, because you're optimizing the error from the previous stage, you're guaranteed that the error will go down. Yes,
Would this qualify as a boosted mixture of expert mode?
there are some relationships to boosting here. Yes. Not sure, maybe somewhere a mixture of experts come in, but this boosting does give you a flavor of, stage-wise does give you a flavor of this boosting type of methods. Yeah.
Well, you can do additive and non-additive in one optimization.
So we're just using additive to show that, okay, so in this stage, this is just a combination of 3 features added up together. This is now non-additive because you're considering A and C, multiplicative interactions and any multimodal interactions. And now you're considering B and C, and now A and B. So this second order function that you learn over here is not just an additive combination of A, B, and C.
But
And-
three types of models can be added up together.
Yes, you can add. I mean, as long as the features are differentiable and you know you can implement them in PyTorch, you can add anything up together, right? So you could add A, B, and C together. You could consider A and C interactions, add them up. A and B interaction, add them up. Everything is still just matrix multiplications and nonlinear activation functions. So it's differentiable. So you can optimize, for example, this loss with gradient descent. Nice. Okay. So nowadays, of course, we know that a lot of these ideas still remain. It's just the backbones of some of these modern models are using transformers. We saw how transformers can be used for text, can be used for images by essentially getting patches of images, putting it into a sequence, putting these position encodings and applying transformer to get visual representations. So nowadays, a lot of these models essentially just use transformers for fusion. But the similar ideas remain. You have, for example, text as a sequence, vision as a sequence, and these transformer encoders are basically learning these pairwise interactions, these pairwise multiplicative interactions. And sometimes it's not uncommon to also see these residual functions. So you keep something that is image only, and you keep something that is text only. So that resembles this additive, unimodal plus some multiplicative interaction in the middle. Something else that has also emerged in a lot of these models is that they always do alignment and fusion together. So this week we're talking about fusion, right? Last week we looked at alignment. So if you look at a lot of these papers, you'll see there's this, I was pointing to it. There's always this alignment objective. So over here, they have this word patch alignment where they try to optimize something like contrastive learning, how every word should be contrastively aligned to every patch in the image. So that's usually some objective that they also train for. You can think of this as really fine-grained alignment because it's at word level and patch level. And then this other alignment objective is more global. This is looking at the entire image and the entire caption. So one interesting thing that's also emerged is the fact that you have global data. You know that this entire image matches the entire caption. So you have a positive pair and you have a negative pair, as we saw last week. So this contrastive loss is easy to define. It's just a positive image with a caption, a negative image and caption. The challenge is in this loss. Right? This loss is at a fine-grained level. The fact that statue represents this patch. The fact that stone represents this patch, for example. And you actually don't have that data. You don't have this fine-grained data at the level of linking words and patches. So this OT is called optimal transport. Essentially a way of saying if I have global pairs, entire image and entire caption, how do I essentially find alignment at the local levels, one word and one image patch? Essentially just searching over all possible pairwise combinations and finding automatically the one that both has the good matching and has a very good similarity. Yes.
What would be the alignment for word and images? Is it possible to combine those together to align to one image? Like stone strategies?
Yes, of course. Yes. Make you think of phrase level alignment. And yeah, this works that are tackling that. It's very useful because nowadays you just do individual alignment. For example, let's say it's a person in front of a car or a car in front of a person. and you only do word level alignment, then you actually cannot distinguish the order of things. And so that's why these modern models still kind of struggle with these compositional examples. Person in front of a car, or car in front of a person, or person sitting on a horse versus horse sitting on a person. Still hard to distinguish. So yeah, so you can train these models and you can see that it's able to do fusion, so you can learn really good image text representations, and it can also do alignment. So you can look at the flowers and some of the patches that it was aligned to actually show the flowers, the rug, and the patch shows the rug. There's another example quite common nowadays. It's called Albert, align before fuse, and this one does alignment earlier. So you have image features, text features. You use the positive negative pairs to do image text contrastive learning, and then you do this, pairwise multiplicative interaction using your transformers. There's combinations of alignment and fusion. Of course, you got to recall all of these are cases where you have two modalities, image and text, where a lot of information overlap is between them. A lot of redundancy is between them. The image caption, they all describe the same phenomena. That's why these alignment-based objectives work. If there's some more unique or synergistic information, you are at risk of this being thrown away by a contrastive alignment loss. Okay. Not all is rosy. Sometimes these models don't work. And in fact, there's many examples that you will see where people analyze this case, what makes training multimodal classification networks hard. And you see a bunch of examples where you think these modalities, so in this case, it's trying to recognize activities. So there's video data, RGB, plus optical flow. I think there's also audio. These two modalities kind of make sense together, right? You want to hear what the person is doing, you want to see what the person is doing. Optical flow basically tracks long-term motion across time. And so you start combining these, but well, some combinations are worse, right? At least they don't improve. So you might have collected a bunch of modalities, spent a lot of time curating data, training bigger models, but sometimes it doesn't outperform these unimodal models. And there's several reasons for this. Most of them, one reason is because of these unimodal bias. One other example is if you train these like visual question answering models, using images of banana and ask what color it is. And because you always see yellow bananas in your training data, you'll just always look at the question, what color is banana, and just say yellow without actually looking at the image. So you give it a green banana, it will still say yellow. And then there's also kind of fairness concerns, like these image captioning models people have shown, it will be image, and you're training the model to take in the image and generate a caption. Right? So the caption here is a man sitting at a desk with a laptop computer. So kind of get it says man instead of woman. And then you look at why, you can look at the attention map when the model was trying to generate this caption. And essentially, throughout the whole generation process of the caption, the model only looked at the laptop. So we just look at the laptop and assume.
The computer.
Okay, yes, computer.
Sorry.
Yes, so computer. So you always just look at a computer and then assume, for example, the gender of the person using it. Yeah, so here same case, right? So it just looks at the tennis racket all the time and generating the caption, and it assumes that because it's doing sports, that's a particular gender. These are examples of unimodal biases where some modalities have more information than others. There's some asymmetry, and therefore if you start training models, it might be more difficult to optimize. So several ways of alleviating it. Natural way is to just rebalance your data set. So VQA first version had a bunch of these asymmetries, and then afterwards, when VQA 2.0 was released, they always had both. They made sure for every question there were both possible images that could give both possible answers. So is the umbrella upside down? You always see yes and no. Where is the child sitting? There's always different locations. So that's one way of balancing the data and also ways of balancing the training. So there's additional training objectives that you can add in to make sure that the gradient flows to both the modalities, right? Because this error occurs when the gradient only flows to one side. The language, it doesn't flow to the vision side. And finally, speaking of gradients, another solution to this, just last thing I'll cover, another solution to this, another problem is that these models, because these modalities are very different, some modalities can learn more quickly, and they start generalizing and overfitting before the other modality has even completed learning. So they all generalize and overfit, underfit at very different rates, which can make it very challenging to learn. And one way to solve this problem was to essentially train your multimodal model while also keeping track of these unimodal models. Right? This is a multimodal model, and you keep track of the two unimodal models. These two unimodal models essentially gives you a baseline to compare what is the generalization rate that is ideal for that modality by itself. So you could compare essentially the rate of learning in this multimodal model with the rate of learning in the independent unimodal models to try to either speed up or slow down the learning in the multimodal model. It's cool, nice idea. But of course, the complicated thing is that now you've got to train 3 models. So not very good. Okay, so these are all open questions. So summary. We looked at multimodal fusion, some very, very important, lots of models being developed today. And the whole idea is to essentially take in data modalities and learn some single joint representation that captures how these modalities interact, and whether there's some common information, whether there's some unique information, and use some weights to determine where the information is, or there's some synergy and you're learning more complicated interactions to model this synergy. And essentially looked at a spectrum, cases where either your data modalities come in already quite homogeneous, or you've extracted features to make them more homogeneous and more semantically comparable, or data that is more heterogeneous or very different from each other. And there's basically a lot of methods. That's the key takeaway. If more homogeneous, you can just do, for example, late fusion, just use them to predict a label, and take some ensemble. We saw additive fusion, which are just additive functions, but additive functions are not as expressive as multiplicative functions that look at pairwise multiplications between features. And that was in 2 modalities. When we go to 3 modalities, you've got to go from matrix multiplicative interactions to these tensors, right? 3-dimensional cubes. And of course, you can go from just one order, just 2 things being multiplied, to higher order polynomials. And these are all great, but these need to be made more efficient. So we saw some low rank examples. And then we saw methods that where the weights actually changed according to the data points. Right? Everything here, the weights were static, just W1 and W2 for modalities 1 and 2. And things here were more where the weights dynamically changed. So gated fusion, modality shift fusion, nonlinear fusion. And finally, we also saw cases where you do early fusion, so concatenate your data and let the model figure things out, and also challenges with that. How do you improve optimization process to make sure it actually looks at all modalities equally? Great. Okay, so to summarize, we looked at several examples. Again, this is meant to be a quick introduction. Whatever you think is relevant to your project, there's all the papers and references attached. And just a reminder on making progress on the projects and reading assignment due tomorrow for the discussion on Thursday. All right, thanks everyone. Yes. Yes, you can either email me or every time after class, 30, 1 hour. Yeah. Okay.
I just need to press approve.